Okay, so our next practice problem we are going to look at is going to be problem 19.4. So this is in the problem section. It's found on page 1362, but I did make a copy here of the problem statement. So what we have here is we have a 32 kilogram block. It's attached to a spring and can move without friction in the slot that we see here. The block is in equilibrium position where we see it right now. It is struck by a hammer, which imparts to the block an initial velocity of 250 millimeters per second. They want us to determine the period and frequency of the resulting motion and the amplitude of the motion and the maximum acceleration. Okay, so let's go underneath and then these are the answers that we should get. But let's set up this problem. Okay. So this is, I'm going to call it, oops, Aaliyah is coming back in. So practice problem 19.4. And again, this is a problem at the end of this section. And this is on page 1362. Okay, 1362. The mass of our block is 32 kilograms. It's giving us the maximum velocity, and this is when that hammer hits the actual block itself, is going to be 250 millimeters per second, which is going to be equal to, we need this in meters per second, 0.25 meters per second. So that's going to be the quantity that we use in our equations. And then they're giving us the K value of the spring of 12 kilonewtons per meter, which would be 12,000 newtons per meter. Okay. Now we need to find the frequency and the period. And in part B, they want us to find that maximum distance that it moves and the acceleration maximum. Okay. So again, we can just go back to our equation sheet and we want to look, okay, what is the formula to calculate the frequency and the period? So we know the frequency to be equal to our natural circular frequency divided by 2 pi. And we know that the period is going to be equal to 2 pi over the natural circular frequency. All right, so we need to calculate that natural circular frequency first. So that is equal to the square root of the K factor of the spring divided by the mass. Okay, now there is only one spring in this situation. So if we look back, we don't have to deal with trying to get an equivalent spring. So we're going to use that value of our spring rate directly. So our K value, we're going to use the 12,000 newtons per meter divided by 50 kilograms. Okay. So our W, what do you guys get? Our natural circular frequency.
Elliot, it's 32 kilograms.
What was that?
Your kilograms, this should be 32.
Mm-hmm. Oh, it's 32. It was 50 last time, it was 50 in the last problem. I'm so sorry. Yep, I've got 32 written down. 32. Thank you. The right numbers.
19.4.
19 point. I did 19.365. And that would be radians per second. Okay. Yeah, thank you for catching that. Sorry, I had 50 on my mind from our last problem. All right, so that's the natural circular, the natural circular frequency. So now we can use that in both of the frequency and the and the period. Now, as we know, we also know that the reciprocal of the period, we can get the frequency. So I'm going to calculate the period first, and then we're just going to take the reciprocal to get the frequency. We could do the same thing in the opposite direction. Honestly, it doesn't really matter. So 2 pi divided by 19.365. Our period should get about 0.324 seconds. And then our frequency is going to be the reciprocal. So our frequency should be 3.082. Now this is cycles per second or hertz. Okay, so again, that's a cycle per second. So the frequency is how often they occur in 1 unit of time. The period is how much time is between each cycle. Okay. So that's part A. Let's check our answers. Hopefully they're the same. They are. Look at that. Now we're ready to look at the second part, the amplitude, which is going to be our maximum distance from our equilibrium point and our maximum acceleration. Okay. So if we look here, you'll remember that the problem gave us velocity, right? So part B, we can calculate that maximum amplitude using the maximum velocity equation that we have. So rearranging this, we know what the maximum velocity is from our problem. We want to solve for our xm. So xm is going to be equal to the maximum velocity divided by our natural circular frequency. So we had 250 millimeters, but we need to use the 0.25 meters per second divided by 19.365, and this would be radians per second. Yeah. Again, just to make sure that we, see what's going on here. Seconds cancel, radians are nothing, so our units are going to be in meters. So our maximum amplitude should come out to 12.9. Sorry, nope. That would be bad. 0.0129 meters. And probably something, it's a pretty small number. It would be 12.9 millimeters. Not that you have to put the millimeters, you want to report in meters, but more relatable is 12.9 millimeters. Okay. Just as a frame of reference. And then we need to find the maximum acceleration. We know that to be xm times our natural circular frequency squared. So we know our xm now, 0.0129 meters. And then we want to multiply that by the 19.365, and we have to square that value, right? Our maximum acceleration, 4.841 meters per second squared. And that's it. And if we peek back, those look like good numbers. There we go. Questions on problem 19.4. All right. I'm going to stop the recording here and then we'll do our last problem.